Okay, guys, so in the previous classes, we introduced laws, formulas which can be used to find which could be used to find magnetic fields. Now the next logical question, all right, how do those magnetic fields interact with the world, interact with the material? And of course, we all know that if you dive inside of the material, we will find tons of point charges, small charged particles like electrons and protons, right? All right. So at the fundamental level, if we know if we know how magnetic fields interact with point charges, then using some additional logic, some additional theories, we should be able to describe interactions of magnetic fields with any complicated material. And of course, we all know the quantity in physics which we use to describe any interaction. It's a force, right? So basically, at the fundamental level, if we know how a magnetic field interacts with any charge, point charge, then again, as I said, using some additional theories, we should be able to describe interactions of the magnetic fields with any material. So as a result, let's start with introducing a magnetic force acting on a point charge. So if we assume that we have some point charge, right, which moves in some external magnetic field, and according to this fundamental equation, which was written basically experimentally, observing the nature, right? It's one of those fundamental equations which cannot be derived. So that force, magnetic force acting on the charge, equals to the value of the charge and the cross product of the velocity of the charge and the magnetic field, So you see, again, most of the stuff in the world of magnetism is sort of the world of magnetism is in dynamics, right? You see, again, for a charge to experience magnetic force, the charge must move. If the charge is stationary and exposed to the magnetic field, the charge is not going to experience any force, right? So the charge must move. And the same with magnetic field production. Charge must move in order to produce a magnetic field. And the same here, charge must move in order to experience magnetic force from a magnetic field, right? And also, so direction of the magnetic force is determined by the cross product of V and B, right? And then quickly you have to check the sign of the charge. If the charge is positive, then direction of V cross B gives us direction of the force. If charge is negative, find direction of the cross product V and B, and then flip that direction because the charge is negative. Right? Okay, so very often this equation is called the Lorentz equation, right, or Lorentz force. Okay, so that is one of the fundamental equations in physics. Then, once you know this fundamental equation, then force acting on the current, on the wire with current, can be easily derived from this equation. Because why? Why? Because current is just a bunch of charges, moving in the same direction with the same velocity, with an average the same velocity, right? So in this case, in order to write expression for the magnetic force acting on the wire, or any wire with current, we have to make a very simple transformations to this equation in order to get equation for the force acting on the wire. Similar transition we've made in order to rewrite Biot-Savart law for a current. You remember we had two forms of Biot-Savart law. Biot-Savart law for a charge and Biot-Savart law for a current. So how did we make the transition? We replace charge with the current and velocity with the element of the current. So here we're going to do the same. So if you replace charge with the current, velocity with element of the current, dl, and cross it with B, that's the formula. for the magnetic force acting on this small section of the wire of length dl, of infinitesimally small length of dl. And you see, dl is presented as a vector. Direction of dl is determined by the direction of the current. So current that way, dl that way. Current that way, dl will be that way. Okay, so again, this can be used for any wire. It doesn't have to be straight. It can be straight, it can be bent, it can be twisted, any wire with current. And then this equation, using this equation, we can apply this equation for a straight wire, force acting on the wire, straight wire of length L. Again, from here to here, transition is very simple, right? So if you do that, so let's assume that we have a wire with current I, and the length of the wire is L, exposed to the magnetic field. Then the force acting on the whole wire is I. Instead of dl, now we have L, and again crossed with B. Again, L, absolute value of L is just the length of the wire, and direction of L is determined by the direction of the current. Again, current that way, direction of L also that way. You see what I wrote? L, direction of L is determined by the direction of the current. Okay, so what we're going to use in our problems? We're going to use this. To use this formula, every time we will, in order to use this formula, we will have to integrate. We're going to skip that. And we're going to use this. So we're going to use this and that in our problems. Right. Okay, so the first problem, the first example, it's a problem 26, still chapter 29, problem 26. Right. So what do we have here? We have a proton, point charge proton, which flies with a certain velocity, given velocity, right? In a certain direction. And of course, that proton is exposed to an external magnetic field. A magnetic field is given, velocity is given, right? And of course, we will have to find the force, magnetic force acting on that proton. Okay, let me get the numbers. So first of all, I have to write that we have a proton. Proton. Velocity of that proton is 1 times 10 to the power of 7 meters per second. Right. Then there is a magnetic field. Magnetic field given in this form. I think it's 0.5. Yeah. 0.5, and it acts in the x direction. You see I hat. I hat, it's a unit vector showing positive direction of the x-axis. And of course units of Tesla. Okay, so now I need, since this is given in a vector form, let me introduce coordinate system. So now it looks like coordinate system is needed. And I will introduce it in this way. All right, so this is my x-axis. So magnetic field will be pointing this way. Then this will be my z-axis. And y-axis will be into the board. It's still right-handed coordinate system. It's still right-handed. I arrange it in this way because it's the most convenient for this problem. So magnetic field is in that direction. So magnetic field is in this direction. So that's B, right? In the x direction. Then this proton flies also in a given direction, and that direction is, it flies in the xz plane at 45 degrees. So that's velocity. And that angle, this angle, is theta equals to 45 degrees, right? Okay, that's what is given, and we just need to find the value of the force, right? I think, yeah, that's what is given. So we need to find magnetic force on the charge, right? So we have magnetic field, charge moving, so there must be magnetic force acting on this charge. In terms of physics, not much to discuss. So we just need to a direct application of this fundamental equation. So there is a charge exposed to the magnetic field. There must be magnetic force. That's what we observe, right? That expression, that formula was written based on observations. So let me just rewrite F equals Q V cross B, right? And so we just need to apply it. Again, force is the vector. So we have to find, probably first I will find direction and then absolute value of that force. So let's start with direction. Direction. Right-hand rule, V cross B. Okay, right-hand rule number one. First you need to align your hand in the direction of the first vector in the cross product. So it's like this, V. And then you need to orient it in such a way so that you can bend your fingers towards the second vector in the cross product, which is B. So B that way. So I have to position my hand like this, and only then I can bend my fingers in the direction of the B vector. And as a result, my thumb, outstretched thumb, gives me direction of the cross product. So which is into the board, which is Y direction. So that is V cross B, into the board. Now you need to check quickly the sign of the charge. Since we have a proton, positively charged particle, so direction of V cross B gives us direction of the force. So as a result, direction is in plus Y direction, right, into the board, right? Okay, and the next step, let's find the magnitude, right? Magnitude of F. So F equals, so you see there is no vector sign on top because I'm talking about the magnitude. So Q, magnitude of V cross B. We all know how to find magnitude of the cross product. It's a magnitude of the first vector, magnitude of the second vector, right? And times sine of angle between them, correct angle between them. In order to find correct angle between two vectors, both tails of both vectors must be positioned at the same point, right? And that's what we have in the picture. Tail of V at the origin, tail of B at the origin, so that is the given angle is the correct angle. So I can write sine of theta. Okay, so basically we're almost done, so we just need to plug numbers, right, and calculate it. Okay, I will write it. So 1.6 times 10 to the power of minus 19 coulombs. Velocity is 1 times 10 to the power of 7 meters per second times magnetic field 0.5 Tesla and sine of 45 degrees. So if you calculate it through, you will end up with 5.7 times 10 to the power of minus 13. Okay, it's just force. The same units like in physics 1, newtons. Electric force, magnetic force, friction, tension, whatever, they all have units of newtons, right? Okay, the problem asks to write this force in a component form, okay? So let's write F. So we know the magnitude and it's all in the positive Y direction. So if I write components in this form, right? So first X component will be 0. Right, then Y component is 5.7 times 10 to the power of minus 13 newtons, and Z component will be 0 because our force is purely in the Y direction into the board. Right. Okay, not much, just to practice again right hand rule, right, and just to practice the equation. That's it. In homework, you're going to have, again, the same problem 26, but it consists of two parts, A and B. We just solved only part A. Right. So now, next, let's look at more complicated examples using practicing this formula. Force acting on the straight wire with current, right? Magnetic force, right? Okay, I need to erase it. I don't want to erase that because we need it for our problems. Okay, right. So the next problem is 36. The same, chapter 29, problem 36. Okay, 3-6. Now we have, it's a problem, idea of this problem is very similar to the example which I discussed yesterday, yesterday in my lecture, right? We had two parallel wires, right, with current, and we found the force acting between them. So now, instead of two parallel wires, we're going to have three parallel wires of some length L, right, and some additional geometry given, some currents are given, and so on. So now problem is more complicated, so let me draw them, right. Probably I will use these colors. First wire is going to be, let's say, black, right. So first wire with current flowing this way, so that's I1. Then the second wire is going to be here below, right. Direction of this current this way, so that is I2. And the last wire is going to be even lower, and the current goes this way, I3, right. The values of these currents are given, they're all the same. So what we have, I1 equals to I2 equals to I3 equals to 10 amps. Then length of these wires are the same, L, and L is 50 centimeters. L equals to 50 centimeters. Okay, half a meter. Then what else is given? Distances between these wires. Let's say this is A, which is, okay, I will write there. So let's say this is A, this is B, and A equals to B equals to 2 centimeters. Right. So they position reasonably close to each other. Right. Okay, so we have electrical part, currents, we have some geometry, and so what's the question? We need to find the net force acting on the current I1. In your homework, you will have the same problem, but you will have to find a force acting on the first wire, then you will have to find the net force acting on the second wire, and then the force acting on the third wire. So, but in this part, let's find F1, right? Force acting on the wire I1, right? Okay, let me check. I think I gave you everything. Yeah. Okay. And now the approach. Before we start crunching numbers and equations, we need to discuss approach. You remember the approach which I used in yesterday's lecture discussing force between two wires. I told you, right? So we need to clearly identify steps. So you remember in that example, one wire, I told you, okay, let's treat this wire as the source of the magnetic field. So one of the wires created magnetic field, and then the second wire was exposed to the magnetic field created by that first wire, right? And then once you know a magnetic field and which wire is exposed to the magnetic field, you can use this formula in order to find the force. The same idea is here. But now we have two wires which are going to create magnetic field. So current I2 is going to create magnetic field everywhere. And of course, at the place of the wire I1, current I3 is going to create its own magnetic field. And of course, there will be some value of the current at the place of I1. So of course, we need to find those magnetic fields, add them up in order to get net magnetic field at the place of wire I1. And then once you know that magnetic field, and we have current I1 exposed to that magnetic field, using this formula, we should be able to find the force, net force acting on the wire I1. So that's the structure of the solution, right? So now let me write it. Okay, I will first write in words. So I2 and I3 create magnetic fields, right? B2 and B3. Okay, let me write B2 and B3, and then I1 will be exposed to that net magnetic field, and I1 is exposed to that B net. So exposed to B net, which is B2 plus B3, right? Okay, so the steps. First, we need to find these magnetic fields, take care of their directions, find the net magnetic field, and then find the force using this formula, because you know magnetic field, you know the current which is exposed to the magnetic field, and problem will be done, right? Okay, so now let's get into the details. Absolute value of B2. It's a basically infinitely long straight wire, right? We know the formula for the magnetic field, B2, so we can write that B2 absolute value equals mu naught I2 divided by 2 pi r, right? 2 pi r, which is r, where is the r is the distance from the wire to the point where you want to find magnetic field. We're interested in the magnetic field at the place where wire I1 is. So wire I1 is at the distance a from the wire I2, which creates this magnetic field. So over here we should write 2 pi a, right? And what's the direction of this magnetic field at the place where the wire I1 is? Okay, right hand rule number 2. Outstretch your thumb in the direction of the current I2, and your curled fingers curled around the wire is going to give you direction of the magnetic field above and below, right? So above magnetic field is going to be into the board, it's a cross. Okay, I will use blue. So that will be our B2. Below, we're going to have dots. In your homework, you will need this. And even here below, we will have dots. So that's B2. That is B2. That is B2, right? So in this case, at the place of the wire I1, direction of that is into the board. Into the board. Right. Then let's do the same for this magnetic field produced by this wire. Of course, at the place of wire I1, we can write that B3. You know what? Let me start it here, right, to have more space. So B3 will be equal to mu naught I3 divided by 2 pi. Okay, at the place of the wire 1, distance from I3 to wire I1, this distance is A plus B. So over here I have to write 2 pi A plus B. So that's the magnetic field strength, B3. At the place where the wire I1 is, because that's where we want to find the net magnetic field, so that we can find the net force acting on the wire I1. All right. Okay, direction. Now let's use again right hand rule number 2 in order to get direction of this magnetic field B3. Again, outstretch your thumb, and direction above the wire is going to be out of the board dots, below into. So out of the board, it means that we're going to have dots, dot, 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 here also dot, dot, and below, of course, we're going to have crosses. So that's B2, 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 B2. Again, just right-hand rule number 2, right? When you curl your fingers around the current in order to find directions of the magnetic field lines. Okay, so you see at the place of the wire I1, directions of B2 and directions of, oh, it's a 3, B3. Why I wrote 2? I have no idea. 3, all right? So you see directions of B2 and B3 are opposite, so they're going to partially cancel each other, right? So the net magnetic field is going to be sort of weaker. Now will be smaller. Okay, so and of course, which magnetic field is going to be stronger, B2 or B3? Of course, B2, because wire, the source of the magnetic field B2, is closer to the wire I1, right? So if the source of the magnetic field is closer to the point in question, of course, the magnetic field is going to be stronger. And even just by looking at the formula, you can say, although currents are the same, I2 and I3, right, 10 amps, but since A is smaller than A plus B, and since A is in the denominator, so of course the magnitude of B2 is going to be larger. So B2 is larger than B3, so as a result it means the net magnetic field is going to be into the board, right? Cross. Okay, so now I can write B, which way I label it? Just B net, yeah. B net will be, since B2 is larger, stronger, B2 minus B3, and direction I will write at the end. So direction of the net magnetic field is going to be into the board, because again, B2 wins. Right, so I can subtract this minus that, right? Mu naught. Okay, I can factor out mu naught over 2 pi immediately, right? Mu naught over 2 pi, right? And what will be left in the brackets? I2 over A minus I3 over A plus B, right? So that's the net strength of the net magnetic field, and direction is into the board. Into the board. Right. Okay, so now we found net magnetic field and direction, net magnetic field strength and direction at the place where wire I1 is, right? So that magnetic field to which wire I1 is exposed. So now we know which current is exposed, I1, and we know the magnetic field. So now we can use this formula, and that wire is a straight wire, so that is applicable. So now we can just use this formula in order to find, it's a final step, in order to find the net magnetic force acting on the wire I1, right? So the second step, the final step. So F1, first I will write it as a vector, in the vector form. So I, okay, that is the current which is exposed to the magnetic field I1, and the cross product of L and B net, right? B net. And you know what, let's again split it into two steps. Let's first find direction, and then we can find the magnitude. Direction of L, you remember, direction of L is determined by the direction of the current. So in our case, direction of L in this case is determined by the direction of I1. So L that way. Then you need to cross it with B. So L that way. B is into the board. So L cross B. I have to position my hand like this, right? So L that way in the direction of the current, then B net is into the board, so L cross B As a result, my net force is going to be upward. Right. So the net force, this F1 is going to be up. F1, and I can draw it also here, F1. And I will write it here also. Direction upward. All right. So now we know the direction, and now what's left? We just need to find the magnitude. So magnitude. F1, again, you see there is no vector sign. It will be I1 times L, then absolute value of B net, and sine of angle between L and B. Okay, that angle can be easily seen. Direction of L, it's the direction of the current. All right, so it's that way. Direction of B is into the board. So direction of L that way, into the board that way. So the angle between them is 90 degrees, right? Direction of L and B, angle is 90 degrees. So sine of 90 degrees is 1. So basically we're ending up with a product of current I1, length of the wire, which is given, and B net, which is, we found absolute value of B net. So mu naught over 2 pi, I'm just rewriting this over here, right, instead of B net. And the difference between this I2 over A minus I3 over A plus B. So that's the formula. That's the final result. Direction is upward. Let me frame it. And over here I can write the answer. Of course, don't forget to convert all these centimeters into meters, right? They must be in meters. All right, and the answer is going to be 2.5 times 10 to the power of minus 4. Again, it's just a force, units of Newton. Newtons. So, direction and absolute value of the force. And you see direction, so that force will be pushed up, right? Pushed up. So that's the second problem. And now we're going to make the next problem even more complicated, right? But again, it will be all about this formula. So in the next problem, we have a rectangular loop with a current which is positioned reasonably close to an infinitely long straight wire. Okay, I will probably start with the picture. Right. So let's assume that we have, this is our infinitely long straight wire with the current, of course. Current I equals to 3.5 amps. Then there is a rectangular loop, and it is placed over here underneath. Right, so let's say this is our rectangular loop. Geometry is given. No, first of all, current. Current in this loop is also given, right? Current is let me label it I1 is also 3.5 amps. So absolute, the strength of currents are exactly the same. But of course, on purpose, I labeled them differently because we will need it. We will need it. We need to identify them properly. Then some geometry is given. This distance is given d, and it is equal to 3 centimeters. Yeah, by the way, this problem is not from this book. I took it from Giancoli, right? Another book. I just like this problem. Then this distance is A, which is 10 centimeters. And this distance is given, and that is B, 5 centimeters. B equals to, okay, it doesn't look like 5 centimeters. Okay, so what we need to find? We need to find the net force acting on this rectangular loop. So what we need to find? F, okay, I will write a vector on the loop, acting on the loop, right? So we need to find net force. Maybe you know what, let me add F net. And again, before we start solving this problem, getting into the details, again, we need to understand the idea. And the idea is similar to the idea of the example which I discussed yesterday in the lecture. And they are similar to the idea which I just used in the previous problem, right? So first of all, you need to decide. So I'm going to use this object as the source of the magnetic field, or this wire, right? And then the second object is going to be exposed to that magnetic field, experiencing a force. So now we have two objects. Since we need to find the net force on the loop, it's a clear indication that we have to treat this infinitely long straight wire as the source of the magnetic field. We can easily find the magnetic field. We know the formula for an infinitely long formula for the magnetic field created by an infinitely long straight wire, right? We've used it so many times now. So we can easily write down the direction and the magnitude of that magnetic field, and then this loop will be exposed to that magnetic field, experiencing a force, and we can use again this formula to find the net force, right? So that will be the idea. Again, that is the source of the field, and this will be the object which is exposed, or current which is exposed to that magnetic field. You know what, I will show this direction of the current everywhere. So this is direction, this is direction, this is direction. Right, okay, so I will write I creates a magnetic field, right? And I can write, of course, the formula for the magnetic field. All right, so B equals mu naught I divided by 2 pi r. R in this case will be different, right? For this part of the loop, for that part of the loop, for this part of the loop. So that's why I didn't specify. So for now, R, it can be anything, right? But that is the formula which we need, of course, to find the magnetic field strength created by that wire. Okay, direction. Direction, right-hand rule. Number 2, again, outstretch your thumb in the direction of the current I1 that way. And as a result, magnetic field lines are going to be circles like this, right? Above that wire, magnetic field is going to be out of the board, which is dot. Okay, which color should I use? Let me use this green, right? So out of the board, dot, dot, dot. Below into the board, so over here I'm going to have cross. Okay, I will draw it, you know what, let me draw it here. Cross, 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 and here also cross, cross, cross. So that's B. It's this direction of this magnetic field, right, which is created by that infinitely long straight wire. Maybe I should even sort of make it green, right? So that's to have similar colors. Okay, now, so this loop is exposed to that magnetic field, and if we want to find the net force, of course, we have to split this loop into 4 parts, right? So this part, first one, let me label it something like this. So first part, then second part, which one I label? Okay, so this will be second part, right? So this straight wire, so this straight piece of wire exposed to the magnetic field, we can use this formula. Then this piece of wire again exposed to the magnetic field, that formula can be used. Then this and that. So we're going to have 4 parts, and we're going to have 4 forces which if you add them up, you're going to get this net force which we need to find at the end. Right? So this will be number 3, and this will be piece of the loop number 4. Right? So as a result, I can write that F net equals to F1. It's a force acting, magnetic force acting on this piece of the loop, plus F2 on this, plus F3 and plus F4. So now, step by step, we need to find all these forces, directions and magnitude, right? And of course, every time we will have to use that formula, right? F equals I L cross B, right? So let me frame it. Okay, I will frame this way. So for each of these forces, every time we have to use this formula, right? Since we have straight wires exposed to the magnetic field, so this formula is applicable. So let's first find directions. I just want to see directions of these forces on the picture. Let's start with this first one, F1. Again, what determines direction of the force? Cross product of L and B. And again, you remember what determines direction of L? Direction of the current. So for L1, that's the direction of the current for this first piece of the loop, direction of the current, so that's direction of L1. So L1 cross B. L that way, B, you see B is into the board, so right hand rule, L, B is into the board, cross it with B, so I have to position my hand and orient my hand like this, so L cross B, so you see, B, and as a result, cross product, direction of the cross product is up, so that will be direction of the force F1. So I can draw it here. So this will be direction of the force F1. It's this, right? Now let's look at the direction of the force F3, this one, lower part. So now current flows this way. Current flows this way, so direction of L that way. And B is still into the board, so right hand rule, first L, then I need to orient in such a way so that I can bend my fingers towards the second vector in the cross product, right, towards B, and as a result net, okay, not net, just direction of the cross product is down, right, and of course that's the direction of the force, so that will be F3. Okay, now let's look at F2 and F3. Actually, before we start looking at F2 and F3, obviously force F1 must be larger than force F3, because this wire, this piece of loop is positioned closer to the source of the magnetic field, so it is exposed to a stronger magnetic field. So magnetic field, this magnetic field over here is stronger. As a result, magnetic force is stronger than here, right? Now, magnetic force, direction of the magnetic force acting on the second wire. So now L is down, direction of the current. You see, current flows down, so that's the direction of L. So L, B is still into the board, so I have to position myself like this. So L is down. Then I have to orient my hand like this, so I can bend my fingers, you see, bend my fingers into the board. As a result, my outstretched thumb gives me that direction. So force F2 to my right. So that's will be force F2. Now the last one, F4. Now current goes up. That's the direction of L. So L is up. Then B is into the board. So I have to position my hand like this, right? You see, like this, so that I can bend my fingers in the direction of the second vector in the cross product, right? So as a result, my thumb gives me direction of the force that way to the left. All right, so this will be it's F4, right? And look, what can you say about these two forces, F2 and F4? They are exactly the same, because all this piece of loop and that piece of loop, they at the same distance from the source of the magnetic field. So absolute value of this force and absolute value of that force exactly the same. But they act in the opposite directions, right? So if we assume that this loop is rigid enough, so we cannot distort it, so just this force will just cancel out this force. They just balance each other out without being able to give us any net force, right? So F2 cancels F4, right? So I can write which way I wrote it. So I can write that F2 equals to minus F4, right? So they cancel each other. I can write, so they cancel each other, right? So I can remove them from my formula, right? So F2 and F4, yeah, F2 cancels F4, right? So will be only two forces left, F1 and F3, and we know the direction, and we also know that F1 must be larger than F3, because again, this piece of wire is positioned closer to the source of the magnetic field, exposed to the stronger magnetic field. Of course, that force must be larger. Okay, so now we know even the direction of the net force, so now we just need to find the magnitude, the strength of the net force. But of course, in order to do that, we need to find absolute value of F1 and absolute value of F3. So let me start with F1, and you see it's absolute value, magnitude F1, because now we know the direction. So now what this formula, this is current which is exposed to the magnetic field. Or you know what? Oh no, it's good, everything is good. Over here I should have put subscript 1, because in all these parts of the loop, current I1 is flowing, right? It's important to keep track of the these subscripts, so it should be I1. Okay, so for this I1 current, then absolute value of L and B, so it's absolute value of L, and in this case, what's the absolute value of L? It's the length of this part of the loop, so which is A, right? So L here, it's in formula in general, L, the length of the wire. In our case, the length of this wire is A, 10 centimeters. So I will remove this L, put A. Then absolute value of magnetic field, this, right? But of course, you know what? I will probably write immediately. Yeah, let me write L, B. And then sine of the angle. Which angle? Sine, which angle? Direction of L, that way. Direction of B into the board. So the angle between them is 90 degrees. Sine of 90 degrees. So that is 1. And why here I started messing up a little bit. B. It's this formula, but now it's a mu naught I divided by 2 pi and r. It's a distance from this wire to this first segment or section of the loop. So this distance is d. So over here we'll have to use 2 pi d. R equals to d, because that's the distance from the source to the point where we want to find the force acting on the current I1. Right, so now let me rewrite it. It will be I1 A instead of B, mu naught I divided by 2 pi d, and sine of 90 degrees is just 1. So that's the formula. We can make it look nicer. We can move factors around. So it's a mu naught I1 times A divided by 2 pi d. Okay, in my opinion, it looks slightly better, right? Cosmetically. So that's the strength of force F1. So let's do the same for force F3. So F3. So we found magnitude of this, now F3. The same, now I1, right? Then A. You know what, let me put here subscript also, sort of like a B at 1 point for first section. Then B at 3 for the third section, and sine of 90 degrees. Again, sine of 90 degrees is 1, right? So I can write it as I1, A. B3, it will be mu naught I 2 pi, and our R, it's this distance. Again, you remember it's R, it's a perpendicular distance from the wire, infinitely long straight wire, to the point where you want to find magnetic field. In this case, it's D plus this width of the loop, which is B. So it's a D plus B gives us a distance R from the wire to the third part of the loop. So it will be mu naught I divided by 2 pi and D plus B, right? Okay, now I can rearrange it to make it look nicer slightly. So it will be mu naught I1 times A, right? And divided by 2 pi D plus B, right? Okay, so we know directions, we know everything, right? I can probably continue over here. Right, I will separate it like this. And now what? So F net, we know the direction of the net force. F net will be equal, we see force F1 up, force F3 down. These are absolute values, so we just need to subtract this from that. This is larger, this is smaller. So it will be a mu naught I1 A divided by 2 pi D. So I just rewrote F1, right? And minus F3. Minus, okay, let me show that this is our F1, right? And the second will be our F3. So it will be mu naught I1 times A divided by 2 pi D plus B. So that is our F3, right? Again, I subtract on purpose F1 minus F3 because I know F1 is going to be larger than F3, right? Okay, so basically, of course, we can factor out plenty. So it will be mu naught I1 times A divided by 2 pi, right? And what will be left inside? 1 over D and minus 1 over D plus B. So it will be 1 over D minus 1 over D plus B, right? So again, don't forget to convert all these distances to meters. 3 times 10 to the power of minus 2 meters, this 5 times 10 to the power of minus 2, and then of course 10 times 10 to the power of minus 2 meters. So if you plugged all those numbers, you will end up with, where is my answer here? 5.1 times 10 to the power of minus 6. Again, it's just force, units of newtons, right? So that's the force. And direction, I will just write in words toward the wire. So that's the, and I will write underneath toward the wire, right? So that's the net force. Of course, this problem is significantly more complicated than the example which we which we discussed in the lecture yesterday. Right. Okay, that's it for today. Thank you.